This webcast discusses problems involving conservation of momentum and collisions, which are also a way of exploring conservation of momentum. Okay, so the first situation here, we have a blue bumper car that hits a red bumper car, which is initially at rest. So let's see here. So I have a blue bumper car, and it comes over here, and it hits a red bumper car. I'm not much of an artist, but just a little diagram to get an idea. At the end of this, the red bumper car, which is 90 kilograms, it was initially at rest, but at the end it is moving forward, to the right, so the final red velocity is 1.5 meters per second. Now the blue car, before the collision, and it's a 60 kilogram car, before the collision, so the initial velocity of the blue car was 2 meters per second. And what we don't know and would like to find out is what is the final velocity of that blue car. Okay, so the thing that I know is that in this system, which consists of this blue car and this red car, momentum is conserved. And so the momentum at the beginning equals the momentum at the end. Okay, in the initial case, the blue mass times the initial blue velocity, that's the blue car's initial momentum, plus the red mass times the initial red velocity, that's the total momentum at the beginning. That should equal the blue mass times the final velocity of the blue car plus the red mass times the final velocity of the red car. Now one of these terms goes away because the initial velocity of the red car was 0, and I'm looking to solve for the final velocity of the blue car, which is here. And so I should be able to just plug in what I know and solve for that quantity. So I have 60 kilograms times the 2 meters per second, that's the initial momentum on the left, and that's going to equal 60 kilograms times VFB plus 90 kilograms times 1.5. And therefore I can solve for the final velocity of the blue car. It's going to be 120 minus 135 divided by 60, and that's going to be negative 0.25 meters per second. So after the collision, the blue car moved to the left. It bounced back in the opposite direction. Okay, let's look at another problem. So here we're doing a homemade cannon demonstration. We have a 1.27 kilogram cannon. It's loaded with a 54 gram tennis ball, and it's on the floor. And I add fuel to it, light the cannon with a match, and it explodes, stuns the class, it propels the ball forward. A photogate measurement determines that the cannon recoiled backwards with a speed of 7.8 meters per second, and we want to know the speed of the tennis ball. So at the beginning, we had a cannon, and the ball was inside there, right? So they're together. But at the end, or after the explosion, the cannon moved back this way. So the velocity final of the cannon was negative 7.8 meters per second, and the tennis ball moved to the right, and I don't know that speed, so the final speed of the ball is a question mark. Okay, so let's see what we have here. I know that momentum is conserved. So the momentum in the initial situation should equal the momentum in the final situation. At the beginning, I had the mass of the cannon plus the mass of the tennis ball, and they were both at the initial velocity, which was 0. So the initial momentum was 0, but that should equal the mass of the cannon times the final velocity of the cannon plus the mass of the tennis ball times the final velocity of the tennis ball. Okay, so therefore I could, since the sum of these two things, the momentum of the cannon plus the momentum of the ball at the end equals 0, I can say that negative, let's see, the mass of the cannon was 1.27 kilograms and negative 7.8 meters per second. And see, the negative here means that I have moved it to the other side. That should equal the mass of the tennis ball. It's 54 grams, which is 0.054 kilograms, times the final velocity of the ball. So I can just solve then for the final velocity of the ball. It would be let me just calculate this. So 1.27 times 7.8 divided by the 0.054, it's going to be 183.44 meters per second. And it's moving to the right at that speed. Okay, so let's look at some elastic collisions. So I'm going to go down to number 4. In an elastic collision, not only is momentum conserved, but also kinetic energy is conserved. So here I have a 2 kilogram ball traveling at an initial speed of 5 meters per second. So here it's 2 kilograms, and the initial is 5 meters per second, and it strikes a 3 kilogram ball that was initially at rest. They're telling me that it's an elastic collision, and so I can just assume that. The balls collide head-on. The second ball travels along the same path as the first. What are the final velocities of the two balls? Okay, so since it's elastic, I know that the initial momentum equals the final momentum, and I also know that the initial kinetic energy equals the final kinetic energy. They are both conserved. So let me make an equation here for the momentum. So I had a 2 kilogram ball that was traveling at 5 meters per second, plus a 3 kilogram ball that was at rest. Okay, so this term equals 0. That's going to equal the 2 kilogram ball times the final velocity of number 1 plus the 3 kilogram ball times the final velocity of number 2. I should have, my subscripts are maybe a little messed up right here. Let me fix that. The final velocity of number 1, 2 times the final velocity of number 1 plus 3 times the final velocity of number 2. Okay, so that's true. And let's see. I'm going to go ahead and just solve for the final velocity of number 1. It would be 10 minus 3 times the final velocity of number 2 divided by 2, which is 5 minus 1.5 times the final velocity of 2. Okay, so I've solved for the final velocity of the first ball in terms of the final velocity of the second ball. Okay, So now I'm going to start working with the kinetic energies. So the initial kinetic energy equals the final kinetic energy. So 1/2 the mass times the initial velocity squared of the first ball. And then there is no kinetic energy of the second ball at the beginning, right, because its velocity was 0. So that should equal 1/2 of the mass times VF1 squared plus 1/2 of the second ball's mass times VF2 squared. Okay, I'm going to replace this with this thing squared. So VF1 squared would be 5 minus 1/2 VF2 times 5 minus 1/2 VF2. Just don't lose track of the math. We're using the FOIL method here. And so I get 25 minus 15 VF2 plus 2 1/4 VF2 squared. Okay, I can replace this. That goes into VF1 squared, and then I'm going to have an equation that only has one variable. It has VF2 in it. Okay, so I'm going to have 25 equals 25 minus 15 VF2 plus 2 1/4 VF2 squared plus 1/2 VF2 squared. So let me simplify a little bit. I'll combine the VF2 squared terms, and I get that 15 VF2 equals 3.75 VF2 squared. So I can divide both sides by VF2. VF2 is going to equal 15 divided by 3.75, which is 4 meters per second. And then I can plug that back in to my equation up there, and I get VF1 equals 5 minus 1/2 times 4 equals -1 meters per second. So I now know both the velocity of the second ball at the end and the velocity of the first ball at the end. So the math gets a little messy, but if you just work with these two equations, the one for the momentum being conserved and the one for the kinetic energy being conserved, you can solve these problems.